Hey everyone, so today we're going to be learning of the calculus of curve sketching. Now, the calculus of curve sketching is not something that we don't, and it's not something that you do until next year in Year 12 Advanced Maths, but it's a skill that's important to know, and it's especially going to be useful when we're considering equations and the graphs of equations of velocity, a displacement, and acceleration. And it's going to be most useful when we're given the graph of the displacement of a function and we have to determine the graph of its velocity and its acceleration, or we're given the graph of a velocity of its function and we have to find the graph of the function of acceleration. So we know that inherently displacement, velocity, and acceleration are fundamentally related through the derivative. We know that the derivative is the rate of change of something, and since velocity, for example, is the rate of change of displacement, then we can say velocity is the derivative of displacement. And in a similar way, since acceleration is the rate of change of velocity, then we can say that velocity or acceleration is the derivative of velocity. And at the same time, since that velocity is the derivative of displacement, that means acceleration must be the second derivative of displacement. So the calculus of curve sketching is one of the most important skills that you're going to learn in this course relating to calculus, and it has many, many applications. But the basics are something like this. If I have a function, f of x, so I've got a function, some sort of graph f of x that exists on the Cartesian plane, then its stationary points and we're going to talk about what on earth a stationary point is, occurs when f dash of x equals 0. In other words, we're saying that stationary points occur when dy dx is equal to 0. The other important thing about a function f of x is that points of inflection, I'm going to talk about what points of inflection mean. Now, there's a bit of controversy as to how inflection is spelt. Old school mathematicians will spell it inflexion, but a lot of newer courses, such as some syllabuses, spell it with a tion. I personally prefer an x, just because how I learnt it. So points of inflection occur when f dash dash of x is equal to 0, or in other words, we're saying it occurs when the 2y dx squared equals 0. Now, there's a special property, there's one more type, and it's called a horizontal point of inflection. Occurs when for x1 both dy dx is equal to 2y dx squared equals 0 at point x1. So a horizontal point of inflection is when both the first and second derivative is equal to 0 at a particular point. I'm going to draw a function now, and I'm going to label its stationary points, its points of inflection, and also we'll see if it has a horizontal point of inflection. So if I draw a Cartesian plane, that's not doing that. Still not. There we go. Finally. Okay, so y and x. I'm going to draw some function. Might go down, might go up like this, might do a bit of that, might come like that. Now that's a bit dramatic, that horizontal point of inflection there. I might make that less defined. There we go. Okay, so this is some sort of function. We should know that that is a x to the power of 4. It's a quartic function. It has 4 intercepts. It can't be any bigger or less than quartic because it has 4 solutions, or 4 real solutions. So Let's label some points. We know obviously that these are my x-intercepts. Right, these are my x-intercepts here. We know that. Right up here, these are my stationary points. I'm going to write SP, stationary point. This is what we call a stationary point. Now, a stationary point is when we know the first derivative is equal to 0, but it's really where the graph changes direction. In terms of velocity, we were talking about when if something goes up and before it starts going down, it must stop. So a stationary point is when, for example, the gradient of the tangent to this point, so that's a tangent to the point. We've learned about tangents in advanced, of tangents to points, which is the definition of a derivative. It's when the gradient of the tangent to the point is equal to 0. And we can see that if I drew a horizontal line here, well, the gradient of that line obviously has to be 0 because it's a horizontal line. So the gradient of the tangent to the point at stationary points is 0. We call them stationary points. Okay. Now, this x-intercept here, I'm going to unlabel that as an x-intercept. Yes, it is an x-intercept, but it's also something else special. It's what we call a point of inflection. So, a point of inflection is a point to which the graph stops becoming concave down and starts to become concave up, or the other way around. It stops becoming concave up and starts becoming concave down. So if we think of parabolas, this would be a parabola that's concave down. And if I looked at this part of the graph, this would be a parabola that's concave up. But at this very point here, the graph stops becoming concave down and it starts becoming a concave up parabola. We call that a point of inflection, and we often say POI, point of inflection. So a point of inflection is when my graph stops becoming concave down and starts becoming concave up. Now, the special thing about points of inflection, well, for example, the second derivative here is less than 0. That tells us it's concave down. The second derivative here at any of these points is greater than 0 because it's concave up. But the second derivative right here is 0, which implies that it's a point of inflection, or where the graph stops becoming concave down and starts becoming concave up. Now, a similar thing happens right here. So this is a concave up parabola, and this is a concave down parabola. But at this very point here, it stops becoming concave up and starts becoming concave down. So it's a point of inflection. But we can see that this is also a stationary point. It's flat. The gradient of the tangent would be this. So this point here is simultaneously a point of inflection and a stationary point. And we call that a horizontal point of inflection. Horizontal point of inflection. So, in summary, if I were to draw another Cartesian plane, at this point here, dy dx equals 0. At this point here, dy dx equals 0. And at this point here, dy dx equals 0. Okay, now at this point right here, d2y dx squared equals 0, and dy dx equals 0. And at this point here, this is actually my point of inflection right here. That's where it stops becoming concave down and starts becoming concave up. This is where d2y dx squared, or y dash dash, is equal to 0. So I wrote a few questions at the top here, if you want to write that down. I wrote a few questions at the top here. I'm just going to copy them and move it down. Copy. So we're going to sketch this curve using the derivative. So the first thing we want to do when we're curve sketching is find its x-intercepts. So we're going to set y equal to 0. So it's x, 6x, oh, we can take out an x squared actually, 6 minus x. So therefore, my x-intercepts at x is equal to 0 or 6. Now we want to find my stationary points. So y dash, the first derivative, is equal to 12x minus 3x squared. 12x minus 3x squared. Make that equal to 0 to get our stationary points. So we've got to take out a factor of 3x. We're going to have 4 minus x. So my stationary points occur when x is equal to 0 or 4. Find the second derivative, y dash dash of x. That's equal to 12 minus 6x. Make that equal to 0. 0 is equal to 12 minus 6x, which makes x equal to 2. So there is a point of inflection at x equals 2. So we're going to write this is my x-intercepts. These are my stationary points. And this is my point of inflection. Now, if your point of inflection was also one of your stationary points, then we would call it a horizontal point of inflection. So we can use this information to graph this function. And actually, what we might do before we do that is we're going to look at our stationary points and find the y coordinates of those stationary points. So we've got 0 and 4. Substitute that not into our derivative, but into the original equation, because we're trying to find the y coordinate. So 0, we're going to have 0, 0. Plug in 4, we're going to have 6 times 4 squared minus 4 cubed, we get 32. We're going to do the same for our point of inflection. We plug in 2, we get 16. So we're going to put all of that information on our graph. My x-intercepts of 0 and 6. I've got a stationary point at 0, 0, and I might put in 4 here, so that's 6. 4 and 32 is a stationary point. And I also know I've got a point of inflection at 2, 16. So that's going to be about here. Now we also know this is we're thinking, is it a positive or negative graph? Well, it is going to be a negative graph, but let's double check. So let's substitute 1,000 into my equation. Putting 1,000 into the original equation, we get a very large negative number. So my graph has to start down here and go up. It's going to turn around at my stationary point, go through the point of inflection, and turn around at this stationary point. It must turn around at all stationary points. The definition of a stationary point is that it will touch here and turn around. That's what a stationary point means. Actually, that's wrong. Not necessary. It's not necessarily going to turn around. That's my fault. But what it will do is we know it's a cubic graph, so it has to start up here and end down here. We also know that it's not going to turn around because there are no more x-intercepts. That's the actual reason why it's not going to turn around. There's no more x-intercepts. We could have a stationary, and in fact, we can have stationary points that turn around. It could go like this and then like that. And in fact, it's turned around there. And that's what we call a horizontal point of inflection. So here we can see that my point of inflection is here. It stops becoming concave down and starts becoming concave up. So that's how we use the derivative to sketch curves. Some important things we're going to note about this, and this is really where it's going to relate to our velocity, acceleration, displacement graphs, is that we notice that my original graph was cubic. It was a cubic function. Its leading term was x cubed. The derivative was x squared. It was a parabola. And the second derivative was a straight line. So when we differentiate a function, we're always going to get the leading term to be 1 less than what we started with. We should know that from our differentiation, learning about differentiation. So what that means is you have a cubic function, its derivative is going to look like a parabola, and its second derivative is going to be a straight line. Now, if you see a graph, how do you know it's a cubic function? Well, if it has 3 x-intercepts, then it's a cubic function. So the important thing about that is that if we see, for example, the graph of displacement and it's a cubic function, its velocity or its derivative is going to be a parabola, and its acceleration, which is the second derivative, is going to be a straight line. If you see an x to the power of 4 graph with 4 x-intercepts, its velocity is going to be the differentiation and it's going to be a cubic function. Its acceleration, which is the second derivative, is going to be a parabola. Okay. Let's do another example of curve sketching. So let's have a go at sketching this one. Okay. So yes, we could do some polynomial division to find the x-intercepts. I'm not going to focus on that. I'm going to focus on just the stationary points today. So y dash is equal to 3x squared minus 6x minus 24. Notice that it was a cubic, and we've differentiated, and this is obviously a parabola. To find its stationary point, so we set it equal to 0. So 0 is equal to 6x squared minus 6x minus 24. I believe we can divide all that by 3, so 0 is x squared minus 2x. 24 divided by 3 is 8 minus 8. So that would factorize to give x minus 4. X plus 2 is equal to 0. Therefore, my points of inflection, my stationary points are at 4 something minus 2 something. Those are my solutions to the first derivative. Substituting that into not my derivative, but my first equation to find my stationary points. So 4 cubed minus 3 times 4 squared minus 24 times 4 plus 5. We get minus 75. Putting in minus 2, we get positive 33. If we take the second derivative, y dash dash is going to be 6x minus 6. Set that equal to 0 to find my points of inflection. 6x minus 6 is 0, so obviously x is equal to 1. So it's going to be 1. Putting 1 into that equation, we get minus 21. So my stationary points are here. My point of inflection is here. Right, so if we go and start graphing our function now. So if we draw a nice Cartesian plane, we want to graph all of our information, so we might go 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, 1, 2, 3, 4. We've got our stationary point at 4, minus 75, so all the way down here. We've got another stationary point at 2, positive 33. And we've also got a horizontal point of inflection at 1, minus 21, so about down there. We might add that information, 75 minus 21, positive 33. Doesn't have to be accurate or to scale very well. It has to be kind of to scale. It doesn't have to be the best. It just has to show key information. Now we want to know, does it start up here and end down here? Or start up here and end down here? We do that by substituting in a large value of x. You might already know what it is because it is a positive cubic function. But if I do substitute in 1,000, I get a very large positive value. It has to start up here, has to come down, turn around at 4, has to go through this point of inflection. We also know it has a y-intercept of 5. So it has to go through this point of inflection. Just do your best. I would always, as you can see, I'm making mistakes. So do it in pencil first. It comes up, and it turns around and comes back down. So that's how we use calculus to sketch something like that. So we've got our stationary points. We've got our points of inflection, and we've got horizontal points of inflection when our stationary points and our point inflections are both equal at the same time. So some key information from that, we might want to say, so for example, stationary points occur when a graph turns around. And that's why stationary points are also called turning points. So relating that to velocity, displacement, acceleration, velocity is maximum, or is 0 on a graph at the graph's stationary points. And that's because stationary points occur when the first derivative is 0. So velocity is 0 because it's the first derivative of displacement on the graph's stationary points. We also might know that acceleration is 0 at a graph's points of inflection. So we know acceleration is the second derivative. So acceleration must be 0 when the second derivative is equal to 0, which is another way of saying that it's 0 at the points of inflection. And the other thing to note is that when we differentiate a function, its leading term reduces by 1. Okay, let's go over now to the exercise. So the exercise, so we've got equations of motion in a straight line. These graph ones are where it starts to get a bit tricky. So we're going to use that information about curve sketching to have a go at these. So for each displacement graph, sketch the graphs of velocity and acceleration. So this is a straight line. It might have equation, say, y is equal to minus 2x plus 3. If I differentiate that, I'm going to get y dash is minus 2. So it's a straight negative line. That's my velocity. The first derivative is velocity. If I differentiate that again, y dash dash is 0. So my acceleration is non-existent. We don't have a function for it. Or you could just draw a straight line along here. It doesn't exist. It's 0. Part B, we've got a parabola. Let's say it's y is equal to, I don't know, x minus 2 squared, which would be x squared minus 4x. Let's say x minus 2 squared minus 2. That kind of looks like that. So it's going to be x squared minus 4x, and then it's going to be plus 2. So if I differentiate that, y dash, I'm going to get 2x minus 4. So I'm going to get a positive straight line, so minus 4, and it's going to go up. Like that. That's going to be my velocity. The acceleration, y dash dash, is going to be 2. So it's going to be a positive straight line. It's going to look like that. That's my velocity, that's my acceleration. So it's it's important to consider these functions as actual graphs, what happens when I differentiate them, and what does that do to my graph. Part C. This looks like a cubic function. So if I differentiate a cubic function, I get a parabola. So my velocity is going to be 0 at my stationary points. So the stationary points of this function are here. Oh, I don't know why that's happening. The stationary points of this function, I might rub this out, are going to be here, here, and here. So that means my graph is going to be here and here. It's intercepts. Now this is a cubic function, and if I differentiate a cubic function, I get a parabola. So it has to look like this. Right. Now if I differentiate a parabola, I get a straight line. Now we know that an acceleration is equal to 0 at a graph's points of inflection. Now this graph has a point of inflection of about, I reckon it's about there. The point of inflection is where the graph changes from being concave down to concave up. So it's going to be a straight line that looks something like that. So that's my velocity. That's my acceleration. Not like that, sorry. It's going to have an x-intercept there. So it's going to look like... So that's my point of inflection, so the x-intercept is going to be about there. So that's it right there. I might just quickly check the answers for that. Hope I'm getting it right. 802. B. What are we up to? C. Yep, perfect. We've got a parabola and then a straight line. Perfect. So let's reiterate why it's a straight line again. If you've got a cubic function, we know we differentiate, we get a parabola, and its x-intercepts are going to be at the stationary points of that graph. Now, if we've got a parabola, we know if we differentiate that, we get a straight line, and we should also know that the acceleration is 0 at the points of inflection of a graph. We've decided that the point of inflection of this graph is right there in yellow, so the x-intercept of your straight line is going to be right at that yellow point, or the x value of that yellow point. Okay, same idea here. This is a 1, 2, 3, a cubic function. Now, we know that its x-intercepts of the differentiation, which is going to be a parabola, the x-intercepts are going to be at when we have stationary points on my graph. So here and here. Now, this is a negative cubic function. So if you differentiate a negative x cubed, you get minus x squared. So it's going to look something like that. Let's just check the answers to be sure. A, B, C, D, yep. So it's a negative cubic function. That's because it's ending down here. So if you've got a negative cubic function, if you differentiate it, let's say I've got y is equal to minus x cubed or something, the differentiation is going to be minus 3x squared. So it's going to be a negative parabola. That's why it's like that. So, and to reiterate again, the x-intercepts of your parabola, or where your velocity is going to be 0, is at the stationary points of your graph here and here. Remember, the stationary points of a displacement graph are where your velocity is 0. Now, if you differentiate a negative parabola, so that's y dash dash is going to be minus 6x. So it's going to be a negative straight line. Now, we know that acceleration is 0 at the points of inflection of a graph. So the point of inflection of this graph is here in blue. So that's when my acceleration is going to be 0. So it's going to be a straight line, x-intercept right there, the x value of that blue point. So it's going to look like that. Okay, let's have a look at that answer. Beautiful. And E. Right, this is a parabola. Let's say its y is equal to minus x squared. It obviously isn't going to be like that, but we're just looking at an example. What happens when I differentiate a minus parabola? Y dash is going to be minus 2x. We're going to have a negative straight line. Now the stationary point of this graph is right here, and we know that velocity is 0. Remember, velocity is the derivative of displacement, so the velocity is 0 is going to be right down there, and it's going to be a straight line down like that. The acceleration is going to be, well, y, it's very annoying. Y dash dash is equal to minus 2, so it's simply going to be a straight line that looks something like that. Now this graph doesn't have any points of inflection, which is why it's a horizontal line. Right. Question number 2. How many of these do we have? Okay. The graph shows the displacement of a particle as it moves along a straight line. When is the particle at the origin? Well, this is going to be, the origin is going to be, this is x along here. So the origin is going to be T2, T4, and potentially T6, but we can't see that. When is it at rest? It's at rest when its velocity is 0. Its velocity is 0 is when the stationary points of the graph occur. We know from our curve sketching that we just learnt about that stationary points occur when the first derivative is 0. So the first derivative of displacement is velocity. Then it's going to be at rest at T1, T3, and T5. The furthest from the origin, that one's nice and easy, T5. Question number 3, when is the particle at rest? Again, the stationary points of this graph are here, here, and here. From our curve sketching exercise, the stationary points occur when the first derivative is 0, and if velocity is the first derivative of displacement, then the velocity is going to be 0 at t1, t3, and t5. When is the acceleration 0? Acceleration occurs at horizontal points of inflection. Acceleration is 0 at horizontal points of inflection, which are here, here, and that's it. So at your points of inflection, not necessarily horizontal, but at your points of inflection, acceleration is 0, so t2 and t4. That's because from our curve sketching work, we should know that horizontal points of inflection occur when the second derivative is equal to 0, and we know the second derivative is acceleration. When is the speed the greatest? Oh, I've done this question wrong again. I made this same mistake in class. This is a velocity versus time graph. So velocity, so this one is a particle at rest, so that's just when it's 0. So it's 0 right here, here, and here. And it's 0, so 0, t2, t4, t6. When is the acceleration 0? Well, that's going to be at the stationary points of the graph. That's because the derivative of velocity is acceleration. So it's going to be t1, t3, and t5. When is the speed the greatest? It's nice and easy, t5. Describe the motion of the particle at t2. Well, the motion of the particle at t2 is when its velocity is equal to 0, because it's at the x-axis. And t3 is when its acceleration is equal to 0, which means that it is slowing down, then speeding up. So it's slowing down here, and then it's starting to speed up there. That's because its velocity is going down, and then its velocity starts to get bigger. Number 4, when is the pendulum at rest? Well, this is a sine graph. You're going to learn later that the differentiation of sine is cos. When is the pendulum at rest? Well, the pendulum is at rest when your first derivative is 0. That's because the first derivative is velocity. So here, 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 and here. When is the pendulum at the origin? Well, it's just here, 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 and here. Okay. How many of these are? Describe the displacement and velocity of the particle for each displacement graph. Well, the displacement we can see in the first graph, it's going towards the origin, then away from the origin, turns around here, goes towards the origin here, and then moves away from the origin here. Its velocity, well, its graph is going to look something like this. It's going to look like that because it's a positive parabola whose stationary point is there. So the velocity is always, its velocity is positive. We might call this t, I don't know, we might just call this x before its velocity is positive, not before x, sorry. Its velocity is positive after x and negative before. And you might also want to say that it's like a multiple of some number. It's a multiple of the gradient of that line, because it has to be a straight line. Part B, we've got a negative parabola. Its stationary point is here, so its velocity is going to look something like that. So we can see that right here, it's moving towards the origin, away from the origin, away. It turns around, and then it moves towards the origin and then away from the origin as we go back down. The velocity, well, before t1, it's always positive, and after t1, it's negative. And that makes sense, because at t1, it actually turns around. So it's going from positive, it turns around, and it starts going negative. Part C. Well, here we can see it starts going towards the origin, it gets to the origin here, starts going away from the origin, turns around right here, it goes towards the origin, now away from the origin, turns around towards the origin, it meets the origin, and now moves away from the origin. If we differentiated that, we're going to have a parabola that's here and here, its intercepts, because the stationary points are right there, so its velocity is going to look something like that. So here we can see its velocity starts to decrease, it starts to decrease, it starts to decrease. It turns around here, and then it's negative because it's moving towards the origin. Now it turns around again here, so its velocity starts to become positive. Part D, we've got a cubic function. So if we differentiate that, we're going to get actually we've got 1, 2, 3, potentially 4. So we're going to have stationary points here, here, and here. And it's actually going to be, it's a negative cubic function. So its velocity could potentially look something like that. So it's kind of changing a lot. So here we can see it's going away from the origin. It turns around here, moving towards the origin, away from the origin, gets to the origin, moves away from the origin, turns around, gets to the origin, and starts moving away from the origin. Its velocity starts being positive, it then turns around here, starts being negative, turns around, starts being positive, turns around, starts being negative. Part E, well, we've got 2 stationary points here and here, so it's going to be a parabola. It's a positive parabola because it's a positive cubic function. And we can see, first of all, with its displacement, it moves away from the origin, turns around right here, starts to move towards the origin, gets to the origin here, starts to move away, it then moves towards the origin and starts moving away again. Its velocity, well, it's slowing down, slowing down. It turns around right here. Now it's negative, getting more negative. Now it starts to slow down, turns around, and then it speeds up. Okay, hope that makes sense.